the conference dinner. So, as just introduced, I will be talking about the extragalactic very high energy gamma ray sky, but I will of course start by shortly introducing how we actually observe very high energy gamma rays. I assume that most of you know this, but so I will keep this extremely short. So when very high energy gamma rays hit the Earth atmosphere, they produce a cascade of charged particles, which travel in the atmosphere with the speeds faster than the local speed of light, and therefore emit a Cherenkov emission that we can then observe from the ground. There are two main methods that we use to observe these air showers. So the first one is so-called imaging air Cherenkov telescopes, which are pointing instruments and can observe only during the nighttime, and therefore have rather low duty cycles. The current generation consists of MAGIC, HESS, and Veritas telescopes that have been in operation for approximately 20 years, a little bit more. And the benefit of the imaging air Cherenkov telescope technique is that because it's actually imaging the showers, it's better to do it's more efficient in doing the gamma hadron separation, and therefore can observe at lower gamma ray energies and with better angular resolution. But as I said, the caveat is that it has rather low duty cycle. It's impossible to talk about imaging air Cherenkov telescopes without mentioning the future first open observatory for the very high energy gamma rays, which is of course CTAO. That you can see here, which is currently in construction. So the first telescopes are already there in the first telescope is already there in La Palma, and also the 3 more are being constructed. And this will be, of course, a major step forward in the field of the very high energy gamma ray astronomy. CTAO will be built on 2 observatories. The northern one I already showed will be on La Palma. The southern will be at the ESO site, close to Paranal, not at Paranal, but close. And the observatory will consist of 3 different telescope sizes. So the large size telescopes, the middle size telescopes, and the small size telescopes to cover the very wide energy range of energies of gamma rays. And as I already said, it will be a major leap forward for the field because it will have the order of magnitude better sensitivity. It will have a better energy resolution and angular resolution. And as already mentioned, it will extend in energy range in both ends. So the LSTs will allow us lower energy threshold that we currently have with the current telescopes. And then with the huge array that we can build with the small size telescopes, it will also extend the energy range in the other end, so in the highest energies. And yeah, it's currently in construction. The first LST is already there in north, and the 3 more are in building phase. And we, of course, very much look forward to the operations of at least the partial array. Then the second technique that we can use to observe very high energy gamma rays from the ground is water Cherenkov instruments, which are kind of all sky instruments, because instead of imaging the air shower, they are actually observing the particles of the air shower, and therefore can also observe during the day, because they don't need the dark night to see this very faint blue flash. The current observatories are Lasso and Hawk, and there is upcoming southern wide field gamma ray observatory coming up in Chile. And this picture is actually a schematic of that observatory. So as already said, it has kind of all sky view. Obviously, it also only sees the part of the sky that is visible from the ground, but but indeed much larger field of view than with imaging air Cherenkov telescopes, and as already said, can also operate during day, therefore has much higher duty cycle. Okay, Then I move on to the science. Of course, there is an enormous variety of the science cases that you can do in the very high energy gamma rays. And this is a very old plot from the time of when CTA was doing the critical design review, so at least 10 years old plot, but still very much valid because it very nicely demonstrates all the science cases that we can do in the very high energy gamma rays. So, of course, in the galactic science, the origin of galactic cosmic rays is very much of an interest to community. But I will be focusing on the extragalactic sky because in 30 minutes it would be very difficult to cover everything. So let's jump into it. So currently the extragalactic very high energy gamma ray sky consists of approximately 100 sources. And with CTA we expect the order of magnitude increase in this number. The very high energy gamma ray sky in the extragalactic very high energy gamma ray sky is populated by a handful of nearby starburst galaxies and radio galaxies. Here you can see their names and of course the beautiful images that of those using ESO telescopes. But in addition to these nearby starburst and radio galaxies, we have seen 5 GRPs, unless I missed one. I think 5 is correct number. But the wide majority is the extragalactic jets from the active galaxies that are pointing at us. Before I go to the sources, then I of course have to say something about the limitations when we are observing the extragalactic very high energy gamma ray sky, because the horizon in the very high energy gamma rays is currently around the redshift of 1, because when the very high energy gamma rays travel into space, they pair produce with optical and infrared photons of the extragalactic background light, and therefore the not everybody who starts their trip from the quasar will actually get to the ground. This is energy dependent, so the lower the gamma ray energy, the further out, the further from the universe it can come to us. So of course with CTA, with CTAO, with the increased sensitivity in the low energy range, we expect to be able to extend the universe that is observable to us in the very high energy gamma rays from the ground. Here, and you can actually use this effect that absorbs the very high energy gamma rays to study the extragalactic background light, and that's one of the very important science cases that we plan to do with the CTAO. And here is the paper we published on it in 2021, but it's we are also working on updating this study with more up-to-date array, with more up-to-date spectra and IRFs. But in this talk, I'm going to concentrate on these most numerous sources on the very high energy gamma ray sky, which are this active galactic nuclei with the jets pointing very close to us. And they, of course, might harbor the supermassive black hole binaries. Actually, for that, I checked how many of I was trying to check, how many of the very high energy gamma ray blazars have been claimed to host the supermassive black hole binary, and it was actually very difficult to find one for which there would not be at least one claim from past history. So I'm actually how I'm going to approach this is I'm going to show you something about a very short summary about all that other variability from the jet. That is noise when you are searching for these periodicities, which might or might not indicate that there is a supermassive black hole binary, because as we already discussed yesterday, the periodicity you can actually produce also just by processing accretion disk as well. Then I'm going to show you a couple of candidates that are very high energy gamma ray sources and have some kind of periodicity and therefore might have synergies. And I'm going to also show you one that could be an interesting for the very high energy gamma rays observations for the future. And then I'm going to say something about the short gamma ray bursts observations with very high energy gamma rays. Oops, I really have to speed up. Okay, so very short summary, introduction to blazars. These are the most extreme particle accelerators in the universe. When they are pointing at us, we call them blazars. They are bright and variable in all wavelengths, and that's why they are also most numerous in the gamma ray sky. And they come in several flavors, so which are different in the synchrotron peak frequency. So this is just the frequency, so radio here, optical, X-rays, and so on. And the most, and then of course in the luminosity, so the most luminous ones are the flat spectrum radio quasars. And the way it works for the very high energy gamma ray astronomy is, of course, that the ones that have the highest synchrotron peak frequency will have also the second peak at the highest energies, and therefore are the most numerous sources in the very high energy gamma ray sky. And can, while the most luminous ones, they have very soft spectra in the very high energy gamma ray band, and therefore can usually observe only during flares, or we see them only during flares. And here is one example of that variability, you know, just a normal, healthy, relativistic jet doing its normal stuff, outburst kind of thing. 2 months of its of observations. In the very upper panel, we see the very high energy gamma ray variability. You see that there is 2 flares, and then there is the moon break, so you don't see anything in between, but most likely between you, it would be in the flux would not be detectable when it goes into low state in between. And outside, we have been observing this source for many years, and most of the time it's indeed not detectable with the current generation of telescopes. And some of these very high energy gamma ray flares are accompanied with flares in Fermi band and in optical and radio, but some aren't. So you can see that, for example, this second flare, there is very little increase in the Fermi band. So this is the normal variability that I was talking about, that is then making it very, very difficult when you are looking for the periodic signals in the light curves. So there is a significant challenge when you are looking for this periodicities in the very high energy gamma ray band. That is that, of course, the IACTs are not optimal monitoring devices, and we have for very few sources we have this kind of a long light curves that you can see here. So this is Markarian 501, which is the one that we have that has been observed since 90s, and in this light curve, and it's detectable by the instruments almost all of the time, and it has been observed since 2005. So this is like 20 years of data. And you can see that even if it is most of the time observable, so detectable, sorry, it has many gaps and so on. So it's very difficult to look at if you compare, for example, for radio or Fermi light curves to look for periodic signal. CTAO KSP foresees long-term monitoring for 15 blazars, and we did show some of the expectations for that in last ICRC, but again, not ideal for monitoring, so that will not be the main part of our KSP. So then jumping to the next point, which was that I wanted to show you some famous examples of supermassive black hole candidates, and coming from Finland, they would take my passport if I would not mention OJ287, which has the optical light curve of 130 years, which shows 12 years of quasi-periodic pattern, and this was suggested already by Sillanpää et al. in 1988 first, and he predicted this major outburst that would happen in 1990, in the end of 1994, and this flare then actually happened. So, and this 12-year periodicity you are supposed to see in this light curve. However, of course, then the observations continue, and this is the optical light curve from our Tuorla monitoring data, and now when you have more observations, it becomes more and more difficult to actually identify which of these would be this 12-year periodicity peaks and what is just the normal healthy life of the jet. Usually a good indication if there is actually a periodicity is that if you can see it by eye, then it's there, and I'm not sure that looking at this light curve you would go and claim 12-year periodicity. So, and I actually, when I did check the slides in the morning, I saw that I did put the line on the wrong place as of because you can see there is, highest peaks, many high peaks. It's very difficult to identify which are supposed to be the 12 years. I mean, there is for the 12 years peak, there seems to be some kind of peaks coming up. But according to the Valtonen et al. Model, they are coming in somewhat right places still, because there is this impact flares and whatnot. I'm not a total expert of his model, so I cannot remember which ones are the actual peaks. But I wanted to mention this because this source was, of course, now with one of these flares, the major flare that you can see here. There was a detection on the very high energy gamma rays for the first time, and it's the first detection of these sources in the very high energy gamma rays, because OJ287 is a low synchron peaked source, so we can only see it during the flares. Everything else is usually just upper limits. And it was already quite soon after this detection was announced that Liko et al. Suggested that there was a possible link between this flare and a moving component that they could see in the jet. And in the recent paper by my PhD student Jenny, we investigated the polarization behavior during this major flare that caused also the very high energy gamma ray flare. And in the millimeter and optical polarization, we indeed see this very strong rotations of the electric vector position angle that indicates some kind of an emission component moving in a helical magnetic field. And then the timing actually indeed fits very nicely that this moving component would be hitting with the standing shock region that already Liko and Müserlis had seen in their VLBI maps, and that would be the case that would have then caused the very high energy gamma ray flare. So if this somehow is supposed to be connected to the supermassive black hole binary model, then it's very clear that we certainly see something already pre-impact, or something pre-impact already sets something to move in the jet. So somehow the accretion must be increasing already before the actual impact between the secondary black hole and the accretion disk. So then the second example, 1553, which has been also mentioned during this conference already. So here is the original Fermi light curve, optical light curve, and radio light curve, I think. Yeah, looks about right. From the Ackermann et al. 2015 paper. And this is actually, this periodicity of 2 years seems to be persistent in the Fermi light curve, so they still see it in the more recent paper. But in the very high energy gamma rays, this is now the more than 10 years of data from MAGIC. You can see that there is just, so much of this normal jet activity going on top of that if the periodicity is there, it's completely hidden by all of the jet activity, from the normal shocks moving in the jet, things colliding with standing shocks and so on. So I wanted to show this rather new, this very recent paper on this very interesting candidate that they find in the radio monitoring using the Owens Valley Radio Telescope, which seems to have a rather nicely sinusoidal form, the light curve. And this red points here is the Fermi light curve, where I wouldn't say that the periodicity would be equally clearly seen, but at least there is some peaks in time that would indicate that there has been at least some flares with similar periodicity. And why I'm mentioning it here in the very high energy gamma ray talk is that this source is actually at redshift of 1.3. So during flares, it should be detectable with CTAO and therefore is of course of high interest also to our community. So as I'm much slower than I expected, I don't know if the good dinner has something to do with it. I already jumped to the summary of the supermassive black holes at the very high energy gamma rays slide. So I just wanted to communicate to you with these few examples that the very high energy gamma ray band is not the main band where you would want to look for the periodicities and therefore for supermassive black hole binaries. But many already known very high energy gamma ray emitting blazars are candidate supermassive black holes, and many more will be within the reach of CTAO. And I showed you only a few examples, but as you probably know, there is an ongoing debate on what fraction of the gamma ray blazars in general show periodicity, because this all other flares make it very, very difficult to perform a periodicity analysis on the light curves. Then I move on to the GRBs. I don't have to make any introduction to GRBs because there has been already many very nice talks about GRBs during this conference. I just want to mention that the GRBs were, of course, the driving force for the design of the current generation of the IACT. So I remember, for example, when we were inaugurating MAGIC, and we kind of thought that, as soon as we turn it on, we will see the first GRB. The expectations were really high. However, it's very quick to give the summary of the very high energy gamma ray observations of GRBs from 2002 to 2018. There were hundreds of observations, but detections at above 100 GeV was this one almost 100 GeV photon seen by Fermi-LAT, and then this 3 sigma hint of signal from MAGIC, which was a very, very tricky analysis. So we actually published it only after there were the actual significant 5 sigma detections from GRBs. But I want to mention this GRB because it's actually a short GRB with rather low redshift and therefore very interesting case. But of course, with 3 sigma hint of signal, you cannot really say much about the physics. But from 2019, then of course things finally changed, and we have been starting to see the GRBs. This is the one announced by MAGIC collaboration in Nature, and where the bottom line here was that with the very high energy gamma ray emission, we are revealing the new emission components in the GRB spectrum. However, I did look up the more recent literature. Here is then more GRBs that have been detected. So this is the one that I was showing you. This is the one by Hess, and this is the boat as seen by Laso. And in the more recent work, it has been debated if it's actually a new component, because this spectra it seems rather flat, while the SSC model would predict a curved spectrum. But the comment was that it might be in contradiction with these observations. So what would we then expect from CTAO in the field of GRB observations? of course, with CTAO, we will have the fast automatic reaction, but that we already have with all current telescopes. The slewing speeds will be very fast, so that, for example, the large size telescopes, they will be in less than 20 seconds at any point at the sky. And then because of the very low energy thresholds, there is the potential to detect the GRBs at all the way up to redshift of 2 or beyond. And I didn't want to give you any exact number because this is still very much work in progress, but we do expect to see few GRBs per year. The plan is, of course, also to perform follow-up of gravitational wave alerts with CTAO. And this is from the work that Green et al. On behalf of CTA Consortium showed in ICRC, in the last ICRC, for the expectations from those observations. So for they simulated GRB emission from more than 2,000 binary neutron star mergers, and then estimated estimated when they took into account the delays before the CTA will observe and the time that CTA will actually be able to spend in that pointing. So this is in the x-axis, which is the axes are completely not readable for you, but here is the delay from before CTA would start observing, and this alert, this delay consists of course, the alert arriving, then the pointing, searching for the large uncertainty region, and then in the y-axis you have the exposure time that would be spent on that part of the time. So here are this is in minutes. So for example, here in this point is 10 minutes. While the delay to get to that point is also about, I think this is like 13, and this is like 10 minutes exposure. And what is shown here in this plot is that for different viewing angles of the GRB afterglow or the jet, how high percentage of the simulated GRBs CTAO would see. And the color scale goes such, obviously, that the lighter the part on the plot, the higher fraction of the GRBs will be detected. So for example, in this case, for the small viewing angle of the jet, what you will with rather small delays in before we get to the GRB after it happened, and the longer we use there, of course it improves the higher the fraction of the GRBs that we simulated that would be actually detectable. And with that, I have reached the end of my talk, and I did put because we did discuss, there was on the first day there was a couple of things about the composition of the jets. I did put a couple of slides on the backup, but as it didn't directly connect with the rest of the talk, you can ask if you are interested. Thank you.
Okay, thanks a lot. Any questions? We have 5 minutes for questions.
Yes, so can you then say something about this composition?
Thank you very much. Yes. So CTA will actually be very, very good in, we have always been claiming that we can nail this down in the very high energy gamma rays to discriminate between leptonic and hadronic processes in the very high energy gamma ray band. But in this very recent simulation by now of course this is PDF, so it won't run. I forgot that. Anyhow, what you can see is that what was discussed on the discussion session the other day, there was a comment about how you can discriminate them in the leptonic and hadronic in the X-ray band. But what is actually even much more constraining for the models is when you are observing with high sensitivity in the very Hertzsprung gamma ray band and in the X-ray band. Now, where CTA plays an important role here is that, for example, for this source, for Markaren 421, it can be, of course, easily observable with the current generations as well. However, we know that in these high flaring states, the emission is dominated by SSC. All the correlations show that. But if there is a subdominant hadronic component, then it should be, of course, better visible in the lower state, when there is less of this SSC on top of it. And Mihail did make very nice simulation to simulate how the correlation would look like, and when we would observe it with three different, with CTA, you can then separate to three different bands the light curve. Then you actually see a very different correlation pattern with the leptonic versus the hadronic one. So I'm very optimistic on that one, that if there is a hadronic subdominant component, then we will actually be able to see it.
Thank you. Very nice talk. There are observations with XP in X-ray polarization on BL-lag, so showing that apparently it's coming from shocks inside the jet or something like this. I don't know what do you expect from this type of observations? I mean, the information that you have from XP, about what you expect in the high energy emission.
Yeah, so IXP observations of the LSP. So there is the exciting observations of the HSP sources with IXPE, where you can see this very nicely. So when you are comparing the X-ray polarization and optical polarization, the X-ray polarization degree is always higher and the optical is lower. There is this lovely gradient that tells you that the jet is the acceleration region is very energy stratified. For the LSPs, like you mentioned, BL-lag, then of course the tricky part is that this X-ray part is actually part of this Compton or the second peak. And in that case, what you would expect is that if there is a subdominant hadronic, so to my best of my understanding, from theory, you expect for hadronic emission that in that case, the polarization in this peak and in this peak would be of similar level. And this is not what IXP is seeing for LSPs. So, I mean, it's just a further evidence to what I was saying, that during the flaring states, at least, it seems that, the leptonic component is dominating all the show. So what you have to see is, this, if you want to see the subdominant hadronic component, then you have to be able to scope it also in the lower state. But, I mean, the flares are very important for many other science cases. Did I answer to your question?
Hi, thanks for that. I was wondering a bit more about this source PKS 2131 minus 021. First of all, I didn't catch the periodicity. What's the length of the period?
4.77 years.
And has it been followed up in other wavelengths? You said it's not been done in the VHE yet, but has it been looked in X-ray or other?
Yeah, so in this paper, they actually show also which I think they didn't put on archive. I think it's coming like this week. So I don't have my radio fan club hoodie, but I'm not involved in this, but they are, this is the radio people. But that's actually a very interesting paper. So they have the optical light curves as well. And you can see this, which I didn't explain when I was showing this plot. They see this shift when the peak is coming. So the period that they see in the optical light curve is similar, has the similar, the sinusoid has the similar period, so it's 4.8 years or so, but the peak comes later. So there is a phase shift, and there is also the phase shift with, here to align the peaks, the Fermi light curve has been shifted by almost 2 years. So please look it up. There is also the previous paper which shows shows 1 cycle less, but so it's this O'Neill et al. But they have much more data in this paper, and they also had some prediction of with the nanograv, showing it with the nanograv sensitivity, where the source is located and so on.
All right, thanks a lot. Let's thank Elina again.